Lovely, recording in progress. Got it, there we go. Welcome both to those in the room and those watching online through the medium of Zoom. It gives me great pleasure to introduce tonight's speaker, who has braved the wintry conditions all the way from the Marquis pub on London Road.
It was a long journey
to the university. And tonight's speaker is Ed McGowan. And Ed is no stranger to those of us in Leicester. He came here for his undergraduate degree, which involved a master's project, a four-year integrated master's. And in that master's project, he started to work on Borrowdale volcanics.
Yeah.
And that sparked an interest which he carried on in postgraduate research as a PhD student. And he's now an expert on Caldera hunting in the Lake District. So in a moment, I will hand over to Ed and welcome him to give his talk and introduce the title in full. Bear with me while I press all the correct buttons in the correct sequence to launch this PowerPoint and the meeting. Those of you at home, please mute your microphones now if you haven't already done so. But please do feel free to put any questions in the chat, and then I'll read them out to the speaker at the end. So without further ado, I shall go quiet and hand over to Ed. Mute. Round of applause for Ed. We shall share the screen. We want to do full screen share, I think. We will go full screen there. We will admit iPad. We will, that's in the right place, and we want it even lower.
Yeah.
And lastly, we shall hide floating meeting controls. Yeah. And I will turn down the lights. Right. Thanks, Ed.
All right.
Have you turned your mic on?
Yes. Brilliant. It's got a green light.
Brian can make people at home as well, so don't worry about that.
Cool. Okay, everybody seems to screen nicely.
Yeah.
Everyone hear me nicely? Cool. So yeah, tonight's talk, I'll be talking about Caldera hunting in the Borrowdale Volcanic Group, which is what my PhD is mainly focusing on. For the first 2 years of my project, which is how far I've gone through so far, I've been primarily taking a geochemistry base to it. So unfortunately, for those who don't like geochemistry, this is going to be very heavily loaded for it. But there will be a bit of field work, a bit of other stuff added in. So, for those who don't know what caldera volcanoes are, I shall explain, because if we're hunting them, it's nice to know what we're looking for. Calderas are a type of volcano that are very different to your typical stratigraphical mountainous peak. They generally form because we have a relatively shallow magma chamber. But when the volcano erupts, it starts to release the magma and generally comes in the form of pyroclastic eruptions, which are volcanic sediments that we can see erupting out very dramatically in doom and gloom style here. But these pyroclastic deposits will end up piling on top of the roof of the magma chamber. And as the magma comes out of the chamber, it starts to leave an empty void. And this leads a lot of overburdening on top of the roof with not much underneath to support it. And so structurally, it will start to destabilize and collapse in on itself. And this creates a nice cauldron-like basin that we get developing, that we call our caldera. After the caldera has collapsed, that's not the end of the story for it. Generally, they go on to form very nice sedimentary basins. We often get lakes forming in them afterwards. And just because the magma chamber has collapsed doesn't mean the magmatic plumbing system underneath has ended. We can sometimes get post-Caldera volcanism, which can generally produce nice little islands in the middle of our lakes. And this is one that I got the lucky opportunity to go out and visit. This is Towel Caldera in the Philippines. In the background, we can see the this mountainous rim here. That's the southwestern Caldera margin. I'm standing on the northeastern margin. We can see how it very quickly drops into the Caldera basin. And we've got our lake with our post-Caldera volcanic island, which is imaginatively named Volcano Island. Not sure if the locals ran out of imagination or they just called it simply that because it makes it easier to sell trips to tourists who come by and they just say Volcano Island. But in 2019, in December, Tal actually experienced some active volcanism when the island decided to erupt. It was mostly a lot of lava, but it also produced a big ash plume that caused immediate evacuation for the locals. And it persisted for quite a few weeks, and the locals started to get a bit bored. They wanted to go home, but the government set the police out to really make sure nobody did sneak back in. Apparently, it didn't stop people from sneaking back in and collecting their chickens, or as one of my friends who lives locally said, that people went back in to steal other people's chickens. They're very good at frying chickens. They're very proud of them. But this caused a lot of fear for the locals of people going back in and stealing their stuff. So as much as people were, not afraid of the ash, but one thing that was keeping them away was outside the Caldera margin, faults started to appear in the road. And this was a sign that there was a lot of lava, well, a lot of magma upwelling underneath, and it was starting to push the Caldera floor up and spread out. And this caused a lot of panic in the locals. They started to think, is there going to be another Caldera collapse because the magma is spreading beyond the original wall? Thankfully, it didn't do anything. It just calmed down. Everyone went back to normal. But this highlights for us volcanologists who love to research them and need to argue cases for funding, that it's important to know what happens at Caldera eruptions, largely because these are very devastating eruptions, and we also want to keep locals nice and calm if we can. So that is a very strong argument for us to research from it. The problem with Calderas, and this is a cartoon cross-section through one, what we have here is the intra-Caldera, which is the inside area, and around the outside we have the extra-Caldera. The problem with studying calderas, one is they are rare, so we don't get to see the nice tourist videos we're getting recently of people capturing the moments volcanoes erupt. So we can't see these live in action, and this means we have to dig into the geological toolkit and look at the rocks of previous caldera eruptions. But in the nature of calderas, when they collapse, they often bury a lot of their own features. And this is a main problem for the intra-caldera deposits. These massive ignimbrites of pyroclastic material, they just bury themselves completely. And these are the ground zero deposits, so they'll tell us a lot about what's going on when it's collapsing. So these are key for us to find out about. The breccias along the side, these form when the caldera walls get too steep and they become unstable and collapse in. So these are very useful, but if we get massive breccia deposits, it collapsed very suddenly, creating a very steep wall. If we get smaller breccia deposits, then we've got a gentle sag as it slowly went down. So seeing them can tell us a lot, but these get buried by the ignimbrites. If a lake forms on top, we get sediments, which then bury the top of the ignimbrites and the breccias. Not only that, but these are forming a lake, so we've drowned everything, which is wonderful. It means that the only thing that we have access to at the surface is well, within the caldera are the post-caldera volcanoes, which are not really much used to study what happened when it collapsed, because these all came afterwards. So this leaves us with two options of how we can go about studying these. Option one is we could drill boreholes into the caldera and dredge them back up, study the cores. Problem is, boreholes are very expensive, and the deeper you dig, the more expensive they get. And these intra-caldera deposits can be several hundred meters. Some of the states go on to 2 kilometers. So that's a lot of money. And if you want to study it properly, you'll have to dig numerous amounts of them to get a good detailed picture of what's going on. So that's not really a feasible option, certainly not for my funding. I can't afford that. The other option that we have is to look at the extra caldera outflow sheets. And in the Philippines, they're digging so many roads around the margin that they're cutting through these and giving us perfect roadside exposures. But there's a lot of difference between the fact sheets that we see outside and inside the caldera. The ones outside tend to be more sort of sedimentary, depositional, and like transportation driven, as the pyroclastic flows are spreading out, not collapsing straight back down. The deposits are much thinner, the breccias in them are much thinner. They don't show you the fault structures that appear as the caldera collapses. We also tend to get a lot of hydrothermal alteration inside the caldera, which tell us a few key features like how shallow the magma is, etc. But we don't get that outside. So if we study the extra caldera deposits, we get only a fraction of the story. This is where we need a third option, which is ancient calderas. These are ones which are old enough that they have been uplifted, exhumed, and dissected, giving us perfect cross sections both through the intra-caldera and the extra caldera deposits. And thankfully, we have some of these. That will disappear. We have some of these just up the road, or at least a 4-hour drive up the road, but you know, it's quicker than a 20-hour long-haul flight to the other side of the world. And these are located in the Borrowdale Volcanics, which is in the Lake District. They are 450 million year old volcanic rocks that formed during the closure of the Iapetus Ocean, when Laurentia and Avalonia were colliding, or for modern geography, Scotland, Northern Ireland colliding into England, Wales, Republic of Ireland. And in that subduction zone above it created an island arc, which led to not only the Borrowdales, but also Snowdonia volcanics as well. And apparently some parts over into eastern Belgium as well, apparently correlate. But in the Lake District is where we'll stick. There are a few calderas which are known. These, when it works. Yeah. So from the literature, we know of Scafell caldera, Langdale caldera, and Haweswater caldera. Scafell in particular has been extremely well studied. We know its history going all the way from the pre-caldera lavas to the caldera forming ignimbrites. Scafell ended up collapsing in a piecemeal fashion, so it collapsed once, and then again in another location, again in another location, and produced a series of several thick, several 100-meter thick ignimbrite deposits that generally go from andesitic to rhyodesitic and then rhyolites at the top, with a few phreatomagmatic eruptions where water got into the plumbing system and coughed out some volcanic deposits. We also have the post-caldera lava domes, and then the caldera lake, which also saw the odd volcanic eruption as well. And then we get into another pyroclastic deposit that was from somewhere else. We know this story because each deposit has been extremely well researched and published on, and together it forms a very nice story about Scafell. The other calderas, though, don't have such a nice story to them. Unfortunately, they weren't researched in as much detail, and so we don't really know as much about them. We don't know, for example, the massive ignimbrite deposits that formed them. Now, how big were these? Where did they come from? So where exactly are these source vents? Where are the caldera margins? And where did they go? How extensive are these outflow sheets? One of the problems when the BGS went out and mapped them in the late 80s, early 90s was they were rushed. And when you're rushed and trying to do it as quickly as you can, a lot of these rocks do look very similar. And if you don't get enough time to properly look in detail at them, you might miss the odd feature. For example, I'm sure if we showed some of our undergraduates these, asked them to describe them, they'll both say they're grey. You can see the odd pits in them. The one on the right has more pits in it. So you could argue maybe that's different, but maybe at the same time, that's just due to exposure. It's been weathered away more. Could just be the way that it is there. Or in the case of pyroclastic flows, they can deposit different clasts in them. So this may be sort of a proximal depositional feature instead of just a generic volcanic one. As it turns out, in this case, the pits are basaltic clasts in them, which were more prone to weathering and got so eroded out. And these are definitely different, and that is a key feature of them being different. But at a quick glance, you could easily mistake them. Therefore, for my project, to try and get around this and to try and double check the mapping, have they been correctly identified as the same one, or did the rocks look too similar and some wires got crossed on the maps? I'm taking a geochemical approach, and so looking at the chemistry of the rocks, not their actual lithofasci features. That's something I'm building onto for future work. But this is actually our old XRF. I don't have a picture of the brand new one. Should have got a picture, but didn't get access to it. If I give this talk again, I'll ask Lynn to pass me on one. But I'm doing a whole rock geochemistry approach. So that means I take a big chunk of rock there and slice it in half so that I can keep one half to look at afterwards, maybe get a thin section of it. But the other half I will take away, remove the weathered surface on it, because I don't really want that alteration in there. Try and get the nice fresh material inside. Crush them in this lovely fly press and get good workout going. Pop them into a milling machine, mix them down into a very fine powder. And then I'll do one or two things with the powder. One is to mix it with some PVA glue and glue my powder back into a rock. This will give me the major elements, the silica, the titanium, which are measured in weight %. And then the other powder I'll mix with some flux, pop them into this lovely automated Bunsen burner, which is so much nicer than the old manual one, I have to admit. And this will give me my trace elements, which are measured in parts per million. Small fractions, but still extremely useful nonetheless. And the idea is that in all of this crushing, milling, homogenizes the chemistry of these ignimbrites. And so these two pellets that I've got, which are about the size of a £2 coin, should have the same chemistry as this big lump of rock. From that, I can go to a locality where I've got unit A and B, get a nice suite of samples, make sure that there's no chemical zonation through them, see if there is any change from bottom to top. Plot them up, element X against element Y, and in a nice ideal world, I'll get two very distinct, very individual clusters that I can then go and say, this is the geochemical signature for unit A and unit B. And this technique is known as fingerprinting because the idea is that the chemical signature will be unique to each of them, just like our fingerprints are unique to each of us. I can then go to locality 2, to some unknown ignimbrites. Maybe I do know what they are, but I want to try a blind test on them. Can collect a suite of samples. This is the fanciest I got with animation, I'm not gonna lie. Plot them up, and we get 2 nice clusters again. And what these clusters sort of draw a conclusion to is that unit A and unit 2 might correlate, or at least there's a very strong chance that they do. And from that, I can then change my logs. So now we know that unit B is the youngest, unit C is the oldest, unit A is correlating through, and tidy up my graphs because nobody wants to look at messy graphs. I will say though that this isn't a foolproof method, so alongside this I will have to go out and look at the actual facies of the rocks, see do they show the same mineral content, same class content, stratigraphically are they similar, or do we just have a repeating chemistry? So this isn't a foolproof method, but it does work as a very good foundation to decide which units deserve more time and effort. Overall, this is a revised map of the geology of the Borrowdales, with purple dots marking localities where other previous projects have collected samples from. We had a few previous master's projects, including my own, that focused a lot on Scafell, and then we started to branch out. And now for my PhD, I've branched massively out and collected samples from all of these light blue dots. And I shall now move on to what I've done with them, or what they show. First one, we'll start nice and small. Langdale Caldera. So what we know about Langdale Caldera is we have the Lingmore Fell Formation, which is the core Caldera fill deposit. And then just outside, we have the side pike member, which is a proximal outflow sheet, maybe just within the margin, probably. But unfortunately, the area has experienced a lot of faulting, and it makes mapping the side pike member any further out extremely difficult because it just vanishes across a fault. We do know that side pike does correlate to the Lingmore Fell due to mapping just over a small series of faults where we can see this green deposit, which is the side pike member, which rapidly thickens over a series of faults, along with its blue sedimentary deposit that matches similar. So that's where we've got to at this stage. Over the years, people have given their ideas of what could correlate to side pike, but they always end it with nobody's looked at the geochemistry to prove it. So we've had suggestions from Rich Brown, who this was during his PhD thesis here at Leicester, suggested the Filmir member because it's a rhyolitic ignimbrite that's highly welded, sort of matches the description for side pike, which is rhyodacite and highly welded. Low water formation is a dacitic 600-meter ignimbrite, which very close to the Caldera. 600 meters being very thick, it's got to surely have a proximal location. Paddy end member is similar to Filmir, it's a highly welded rhyolite, and stickle pike is a welded dacite that nobody suggested correlating. I just collected samples of it because we wanted to see, could we tell the difference between all of these units? Does this method actually work? So let's see. I know this is where I got all my samples from as well. So this is what the chemistry for the Lingmore Fell and the side pike look like. As you can see, the side pike doesn't overlap entirely with the Lingmore Fell, and this is due to the fact that we don't see the bottom of it. So we believe that the samples which would match up to this are unfortunately all buried. So this is one case where the outflow sheet is actually really useful because we get the complete stratigraphy through it. So we have something to match it to entirely. Starting north and heading south, we'll see which ones hit their target. Filming member completely misses. So unlikely that this one correlates to Langdale. Doesn't rule it out entirely, but it's a strong case to say no. Low water, again, missing the target. Paddy end member, now we got a questionable case. It's not matching up to the Lingmore Fell, the Caldera deposit, but as I said, half of it's buried. And what we're seeing is that the Paddy end member is matching up to the lower half of the side pike. Because thankfully this actually works stratigraphically as well as just randomly plotted on here. The stickle pike, that also overlaps, not only with the Caldera fill, but the upper half of the outflow sheet and a bit with Paddy end. So what's kind of going on here? What matches? Is it a case of 1 or 2? Well, the other approach that you can take is doing a geochemical profile. This is looking at how the ignimbrite changes as you go up it. In this case, we've got a plot for zirconium over titanium, which actually works as a proxy for silica. So we start off rhyolitic and it very nicely zones into a dacite to the top. If we overlay both the Paddy end and the stickle pike on top of this, what we see is the Paddy end very nicely matches the lower half of the side pike, and the stickle pike very nicely matches the upper half. Not only this, but if we draw a line, split it into 2 ignimbrites, the 2 field pictures of both of the side pike ignimbrite from side pike, and the sample here was collected at the top of this cliff. And if you go to the top of it, you hit a grassy patch that goes across and is actually this one. And then the bottom sample here matches the bottom of this cliff and it continues up. So not only do we get a topographical change where we get a nice flat and then to a second crag at the point where the chemistry changes, but it's a little bit tricky to see on the pictures, but the lower half is a very nice pinky color. It's a very welded ignimbrite where the Fiamme clasts, which are welded pumices, are much more elongated. So it suggests that it was a lot more welded. Am I right? No, it's the other way around. They're less welded in the bottom. Then we go to the top where they're creamer, and these ones are more welded. So we also see a color change, which is highly likely reflecting this change in chemistry, and also a welding intensity change. And this welding intensity is actually something that one of our master's students is currently looking at. So I didn't look at it in too much detail because I didn't want to double back on his data. Hopefully I'll just borrow that once he's written it up and use it as further evidence to support this hopeful conclusion that the side pike member, which is often used as one to showcase people because it's nice and easily accessible, isn't 1 ignimbrite, it's actually 2. And what this does for our geological map is we've got the short outflow sheet from Langdale now stretches a good solid 15-16 kilometers down the Coniston Fells, which is much more realistic of what we'd expect from an ignimbrite like this. There we go. Earlier outflow sheet for Paddy end, followed by a second one for the stickle pike. Moving on to Haweswater Caldera. This is one that's been long argued as it could be a part of Scafell, it could not be because the descriptions keep saying it's like Scafell, annoyingly repetitive to the point where my supervisor Mike Branny said, well, maybe it's just an eastern extension of it. So I went out and had a look at that, and I can say they do seem quite chemically different, but I won't be covering that because instead a different hurdle came up beforehand. Haweswater Caldera is primarily made up of two eruption deposits. The Scale Howe Formation came first, which is light blue, followed by the Welter's Knot Formation, which is dark blue. And this is the main caldera forming ignimbrite, but when it collapsed, this is what it produced. And on the generalized succession for it, it's a very large voluminous ignimbrite, which is also the main argument for there being a caldera here, that we've got this massive deposit that surely should have produced a caldera. But there's some slight problems with that. Because I went out and collected a lot of samples from all over to see, is it the same east and west, north and south? And what I found is splitting straight through the middle, there's this fault zone. And all of the deposits on the east of it, as well as this outlier, which does transition from one to the other. But primarily, all the eastern deposits create this nice little cluster that we see, whereas all the ones from the middle of the fault zone and to the west produce a very different chemistry. And it's a nice plot that I can actually explain on this one, that, as I said before, zirconium over titanium is a silica proxy. So the eastern samples are rhyolitic, the western samples are dacitic. So chemical composition there, magma typing there. But then we also have a big niobium yttrium split. And this is actually caused because of volcanic garnets, which are present in some of these rocks. All of the ones to the east are very rich in garnets, so they have a very high yttrium level in them. Whereas the ones to the west are very poor in garnets and barely have any. And garnets in magma are very good geobarometers. I do argue with the data that they say of where they form, but the general agreement is they form from depth. So what we have here are two different magma reservoirs, one rhyolitic and at depth, the other dacitic and much shallower. And so this is, well, sorry, I haven't seen anywhere apart from this case where there's a slight change from one to the other, but it's not a gradual, it's a very dramatic shift from one to the other. And there's a lot of grass covering the contact as well, which doesn't make my life easy. But there's such a drastic change in the chemistry, in the magma type, and the conditions where these magmas would have formed, that I can't keep saying that the Welter's Knot is the same as where it's mapped out to be. Instead, I propose a western sample to get changed. And what we have is Scale Howe, the place fell, which was its pre-BGS mapping name, and the Welter's Knot. How they do directly relate to each other, I've only found this loose correlation in this south one. Hopefully, I want to check this bigger block out and see if there's more evidence hiding in those hills. But move on to another one, the Lincoln Tarns Formation. This is the most widespread ignimbrite in the Lake District, apparently covers an estimated area of 500 kilometers squared. Maybe it comes from Helvellyn. People have suggested the ideas, but no one's confident enough to say yes. And I think I know why. So I've collected samples from a westernly horseshoe shape. This summer, I hope to collect the easternly horseshoe of that to make sure things still match up on the other side. Now that I've created a hypothesis, I know that they're not going to match because that's what science likes to do, throw a spanner in the works. But what we see in these samples, again, sticking with this same plot as well, I will say I can produce these trends on other plots, but just for the case of showing you nice, clean examples, I've used the best cases. But the northern samples up here create a very nice cluster, whereas the southern ones create a very separate cluster too. And again, like before, what we can see is that they're both dacitic. One's slightly a bit more dacitic than the other, but the northern samples, again, are garnet rich, whereas the southern samples are garnet poor. And this was also, the southern samples were the ones that I showed earlier with the basalt inclusions that have been weathered out. And these are things that we don't see in the northern deposits as well. So just like with the Welters Knot, this makes me believe that instead of one big ignimbrite, we've now got two. And this is tentatively suggested. I need samples to prove it, but even so, it works. But it does also help clear up ideas, because it suggests that the orange Lincoln tarns in the north probably came from a caldera hiding in Helvellyn, whereas the creamer Udale, which I've reversed it back to its pre-BGS mapping name, might actually come from a completely unmentioned caldera in Ambleside. So doing a summary of how this geological map has changed based on my data, we have the Langdale outflow sheet, which has now helped to correlate and establish shit stratigraphically. So we now know for sure Langdale is younger than the Scarfell deposits, which is purple ones, but are older than what will eventually become the Udale deposits. The Haweswater deposit, we've now split the main caldera forming ignimbrite in two. So does this mean we've got two calderas? Do we have one that has a more complex history than we thought? Or do we have none at all? And I'll explain my reasoning for none in another slide. And then we also have the Lincoln tarns split in two with a potential northern caldera in Helvellyn and a southern one in Ambleside. And so I'll explain my reasoning for why I think there's potential calderas here or not on a table on the next slide. But just to give context to that table, Haweswater is going to be referring to these dark blue units, Haweswater to the mid blue units. Helvellyn is going to be referring to the blood orange, and the yellow. There may actually be two calderas in here. I'll collect them together because easier. And Ambleside is the cream ones. So this is going to be my field work for the summer. A lot of hiking around, a lot of good exercise. But I'm going to be taking a shift away from the geochemistry and instead looking for physical evidence that we can find in the field to say there was a caldera here. So this is a list of features that generally are mentioned in Lippmann, his 1984 and 2000 publications, but also a lot of other caldera papers where people argue they found one because they found these features, although they generally tend to reference Lippmann, so it's a full cycle round. But if we look at these so far, the green cells are ones that I've already found this evidence before in previous field work. The grey cells are filled in based on what I can find in the literature. So it'll be my aim this summer to try and fill as many of these in with green that I can say I've seen it myself with my own eyes. But we'll go through Haweswater and Haweswater at the moment. What we can see for the intra-caldera facies, there is a massive welded ignimbrite in the Haweswater area, which is over 200 meters thick. Maybe one in Haweswater, it's in that massive block that I haven't checked yet, but everything else is thinner than 200 meters, so it might not be thick enough to be considered properly voluminous to have caused a caldera. The meso and mega breccias, those ones I mentioned at the start about the collapsing caldera walls, don't see any of them anywhere in the Haweswater area. Hydrothermal alteration, that's generally from shallow magma, which remains in the chamber, or if any magma's come back up again and keeps things hot, the water will percolate through, become enriched and cause either alteration, which is generally epidote, chlorite, sericite, silica, very common in the Lake District, not very common around Haweswater or Haweswater. There is a small tick for Haweswater because there are some copper mines around the area, and they generally associate copper mineralization in the Lake District with calderas. Why? I don't fully understand, because the biggest copper mine in the Lake District is by Coniston, that shows no caldera evidence there. Also, the copper mineralization is meant to be dated sort of 30 to 60 million years post Borrowdales, so after the calderas collapsed. And Littman says that these can go on for millions of years after. The longest one I found is 14 million years, but these are 2 to 4 times longer than the longest. So I gave it a tick just for pity's sake, but I don't believe copper is the strongest argument to say there's a caldera there. Silicic lava domes, so these are the post-caldera volcanic eruptions, the islands. Don't find any around here. They may have been uplifted too much and eroded away, maybe, but we'd still at least expect to find the feeder pipes to them, and there's none that I've found at all or read about. There are some lakes though, but the ones in the Haweswater area, they say that they're quite thick, but they're also inflated with sills, and they don't mention in the literature how thick these sills are. So they say it's like 200 meters thick with 3 sills. And the one that I've seen, they say it's 100 meters thick, but you take out the sill and it's only about 20 meters of lake sediments. So not the deepest, and certainly not compared to like Scarfells, which is over a kilometer thick of lake sediments. So I put a question mark. Again, I feel that that's more of just giving pity points to it. Thin ignimbrite sheets for the outflow. This isn't the strongest case argument because all you need is an ignimbrite, but they have them, so ticks, okay, fine. Columnar jointing, this is apparently indicative of outflow sheets, and we never find them in a caldera, only in the outflows, but we don't see any around here. And the proximal lithic breccias, sometimes instead of collapsing in, they can also get blasted out a little bit, but not seeing any major proximal lithics breccias at all in the Haweswater area. Abrupt thickness changes. No, this generally is meant to show you the point where you go into the caldera margin. There are some in the Haweswater area that literature has previously argued. They said one went from 10 to 90 meters thick over some faults very quickly. Turned out that distance was about 300 meters, which is not what I would call abrupt. Complex arcuate faults with pre-caldera next to sin-caldera deposits that would show a lot of subsidence down into it. Not seeing that generally either. There are some rotated fault blocks in the Haweswater area, and ring dikes as well. When it collapses down in a ring shape, the faults tend to get exploited by magma, which forms ring dikes, but we don't see any of that. Looking at the Helvellyn and Ambleside area, we can go through this a bit quicker because I don't have to explain as much, but thick, massive ignimbrites in the Helvellyn area. I showed that there were 3 units around there. One's over 300 meters thick, another's 250, the other's 400 meters. That ticks it off for all 3 of them. The Ambleside area apparently has some which are 800 meters thick. So that's incredibly thick, and something has got to be going on there to produce them. Although I also need to double check their mapping as well, but we'll see. Mesobreccias, there's a lot around the Helvellyn area, in particular just north of Helvellyn. There's 200 meters thick of mesobreccias, and there are some in the Ambleside area, because before the Udale tufts were known as Udale tuff and breccias. So they're somewhere around Ambleside, but I need to go and see exactly where and how they relate to the faults and to the thick deposits as well, because the ones I've seen are just outside in the thinner deposits. But no megabreccias, although I have been told these are extremely difficult to find, so maybe that's the reason why I'm not finding them, because I don't fully have it understood. Hydrothermal alteration, there are a lot of silicic nodules in the Helvellyn area, but you don't see them just outside of the Helvellyn area, just west of the Coniston Fault. There's also a lot of lead and zinc mines, which are commonly associated with cold areas in the US. But like the copper, these actually post-date the volcanism by 60 to 90 million years. So they're even younger than the copper, which I already disagree with. But we still see the silica nodules, so that's fine. Ambleside, I have seen some things in the deposits which look like they could be fluid pipes going through. But I'm not entirely sure. I need extra eyes to double check on them. So I've given it a question mark. Silicic lava domes, there are quite a few, both around Helvellyn area and also around the Troutbeck area, for both Helvellyn and Ambleside. And lake sediments, there's actually 2 in the Helvellyn Basin, which is why I believe there might be 2 calderas there. And then we've got Ambleside has a smaller one, but there's apparently 100 meters of sediment there, so that's looking good. Thin outflow sheets, yes, but I said that's not the strongest argument. Column jointing, there's actually several locations through the Coniston Fells in the Udale formation that has column jointing, so that's good. And proximal lithic breccias, there's both cases just outside in the thinner deposits. Abrupt thickness changes. I've seen the Filmir member in Helvellyn go from 50 meters, crossed over the Coniston Fault, it was over 300 meters. So that's much more abrupt than what I'm looking for. In Ambleside, apparently the Udale formation, from what the literature says, goes from 800 meters to 450 meters over a few faults. So that's a very good, massive drop of 400 meters that we just lost the ignimbrite. So that's a good abrupt thickness change. We got some pre and syn Caldera deposits in Helvellyn, where they actually meet up with the pre-Caldera lavas against the lake sediments. So that shows there's been a lot of subsidence around the area. Rotated fault blocks, yes, for Helvellyn. Ambleside, I have to admit, the maps get messy around that area, so it's a bit confusing to see if they're being rotated or not, just because there's so many lines. And ring dikes, I haven't seen any obvious ones, but who knows? Maybe they just didn't get preserved. They might have got eroded out as it all collapsed and just got rid of the evidence for them. But even so, this is my future plan and what I'll be spending a lot of my summer trying to do and find the evidence for these. But summary overall so far, geochemical fingerprinting has shown positive results. We can tell apart a lot of these ignimbrites one from the other with relative ease. This has caused some of the major units that have been previously mapped to be split in 2 and reclassified, which is creating a more complex stratigraphy, but it turns out that's actually a good thing because it makes things a lot more cohesive and actually understanding. We're not getting a random ignimbrite, but we don't quite know how it matches. It now actually seems to fit into place. And it might be due to the fact that we've got more Calderas than we previously thought in the area. I'm not too sure about Haweswater, if there is a Caldera there. I'm not confident on it at all. But there is at least one Caldera, possibly two in the Helvellyn area, and another in the Ambleside area. So that's what I hope to find and prove at least. And final shout out to everyone who's helped me along my way, because PhDs are not solo projects really. So shout out to my supervisors and to anyone who's helped discuss things with me and clear up some very confusing rocks. To anyone who's joined me out in the field, to the university technicians who put in far more effort than they get credit for, and to literally anyone and everyone else, especially to Clive Bolter as well. Retired geologist in the Lake District. He was actually the one who suggested to the Cumberland Geological Society that I give this talk in the first place. And unfortunately, he died about a week before I could give this talk. So he helped me out a lot for my project and gave me a room to stay in, especially when it was too wet, and helped as much as he could, far more than he ever needed to. But because of him, I'm here today giving this talk to you. So shout out to him. Any questions?
Thank you very much indeed, Ed. I'll take over the microphone again. It's a bit loud, isn't it? We can stop sharing, so you'll see us. We'll remain distant, but hopefully you'll see us in the back of the room. Indeed, any questions either in the chat or from here in the room? Let's stick around the room. I have got some ideas. If anybody else wants to pose a question? I'll start us off. Right, paint a picture. 800-meter thick ignimbrite, if the mapping checks out. What sort of eruption does that come from? You know, is there anything in our experience that would compare in scale?
So a lot of them in America, from what I've been reading up about, they can have 1 kilometer thick deposits. So it is on the scale of them. The Scarfell ones, the 3 main deposits got lumped together as one formation, and that together spans about a kilometer. So we're looking at that sort of scale, but on one eruption. But it could be a case like Scarfell, where it was actually a series of them, and they just haven't been properly segregated. But so far from what I'm seeing in the chemistry, they do create a nice tight cluster, where Scarfell, I can pick apart each unit, so I can separate it timescale, but it's looking on that sort of larger scale.
And larger scale means a lot of stuff into the atmosphere and really widespread effects.
Yes.
This would not go unnoticed.
No, definitely not, and not anything you want to be nearby. As much as I really want to see a pyroclastic eruption, I don't want to be anywhere near one of these when they go off, because people argue you can go to a safe space. It's not really a safe space with a pyroclastic flow to be confident. With this, there's no guarantee of a safe space at all. It's, you're screwed. Watch from space and it'll be safer.
Watch from space, that's okay. That's what we know we need to do if we hear one is on its way. Right, there's a question in the room. I will deliver the microphone to you if you would like.
Thank you for a very interesting insight into parts of the Lake District I know from walking, not from looking at geology. Much easier to do it, to visit without nose to the outcrop, as it were.
Can guarantee.
But I'm interested, you seem to have a lot of emphasis on welded ignimbrites. Are there non-welded or less well welded ignimbrites in amongst these deposits as well?
So at this point, they have liquefied so much that they are all stuck together. Like one that I visited in Mexico, we could literally just scour away with a rock hammer, so definitely unwelded. But I would believe a lot of them do have fiames. They do have heated, squashed and stretched pumice fragments in them, which do suggest that they were hot enough to weld. And it's generally based on how stretched the fiamme are as to how welded they are, as well as looking at the matrix as to how melted that's become. So it's generally a case of we got highly welded and lesser welded, and a spectrum throughout. But I haven't found any so far which are unwelded. Yes. Yeah.
Thank you very much. You've inspired me to go away and look again at publications on the lake sediments.
Yeah.
So now this might be way off topic, in which case just tell me, because I know. But non-marine deposits before the Silurian are pretty few and far between. I work on Cambrian marine things, but I'd be fascinated to know what's happening in Cambrian and Ordovician non-marine environments. Do these lakes have a marine influence? Are they non-marine? And what was living there? And would you expect them to be nice places to live or not? So it's 4 questions in one.
So marine involvement, I don't know of any direct involvement in them. We probably were close enough to the coastline as the Iapsis was closing, so it should be close enough, but how close, I don't quite know. There is a lot of evidence for water. There's a lot of phreatomagmatic eruptions. There's a lot of accretion in the pili, which is ash pellets that form as moisture causes them to stick. So there's a lot of water. Whether it's fresh or salt water, I can't say. Fossils, none have been properly recorded in the Borrowdales. There's one case I know of a trace fossil, but I'm no expert, so I don't know what it is. Would it be a nice place to live in? I wouldn't really say so. I mean, you've seen the slabs that we have on our wall, and they show a lot of soft-state deformation. So there's a lot of turbulent floods into these lakes. There's a lot of evidence of earthquakes disturbing them, and also a lot of other volcanic eruptions coming in and depositing into the lake. So it's a very turbulent place and a very fiery place as well. So I don't think even the water is safe.
Right, thank you. So yeah, I don't think the prospects are good for finding microfossils, for example, but even if we did, they wouldn't probably be representative of Ordovician lake systems in general. Now I see in the chat we've got a question from Mike Howe that I can read out to everybody. Mike says, very nice work. The analyses clearly needed a lot of resources, and could you have separated the flows using a handheld XRF from a clean surface?
This was one thing that I really wanted to do because the department recently purchased a handheld, and so I thought that would be a brilliant way to test it and see how these work, and B, just to play around with a new piece of kit, and also it saves me lugging down massive chunks of rocks. So it would have been great, but when we tested this, what we did was we got, this was actually really useful because the XRF went down temporarily, so it delayed me getting my results back. So I argued a handheld. What we did was we got some standard reference material, but we know from the lab-based XRF what the data is, and we scanned them with the XRF. And we also got some of my older samples out that have been run on the lab-based and scanned them with the handheld. And what we saw was, particularly as the element concentration increased, there was a lot of drift between what was being recorded by the handheld and by the lab. And it got to the point where, particularly on some of the higher concentrations for some elements, the drift was so much that not even error could cause them to overlap. So you could get the same trend pattern, like from SciPy, we could see the same zonation pattern, but we'd have one line here and we'd have another line here, and the error bars were not causing overlap at all. So it wouldn't have been accurate enough to say. And it seemed like a case of, if I used purely handheld, I could create a nice data set that was comparable, but handheld versus lab-based, the two data sets weren't comparable enough for one we had. No,
Unfortunately, no is the answer. Interesting. Thank you very much. Right, I shall have a final look in the chat for questions, final scan around the room. If there are no further questions, let me just make some announcements about future meetings. So please join us for our AGM. That's combined with a members' evening, and that's on the 29th of March at the New Walk Museum. And we won't be having a Zoom link for that. So please attend in person if you can for that largely social event. And please do come along to our joint meeting with the parent body. So that will take place in the New Walk Museum. And the talk will be delivered by Professor Lynn Frostick on the topic of flood risk management. That's on the 3rd of April. That's on a Monday, not a Wednesday. So if there's nothing else, I shall now close the meeting and finish just by thanking our speaker, Ed, once again for a fascinating talk. Thank you very much, Ed. Thank you for coming, everybody. Have a good night, wrap up warm, and see you at the next meeting, the AGM and members' evening.